Rewrite this equilibrium expression, solving it for ClO2F2. I'll show you why we're doing that if you don't see yet in a second. So I'm just going to rewrite this thing and say, okay, that's the same thing as saying ClO2F2 concentration equals K, the equilibrium constant, time. I'm just multiplying both sides by the denominator. This is an expression for ClO2F2. Can I then replace this with what that's equal to? Yeah. If that's the same thing as that, then I can replace the ClO2F2 with what's over there. So the rate is equal to K times the capital K, which is the equilibrium constant. I know a lot of people are turned off with all these Ks. This makes it even worse. Times ClO2 times F2. If your slow step involves an intermediate that was produced by an equilibrium, which this is, that's what you're going to have to do. Now, when you look at this K times that K, do you agree that that K is a constant? Do you agree that that K is a constant? So if you multiply them together, you still get a constant. Yeah. So that's equal to some K. I'm going to call it K prime because the number has changed, but it still represents a constant, times ClO2 times F2. And that is equal to the rate. Now that I made that substitution for my intermediate, does that look more like what we're hoping for? It does. So that means that this mechanism, mechanism number one, although it didn't look like it at first, is a valid mechanism. It's at least possible. Because, for two reasons. Number one, they add up to the overall balance equation. Number two, the rate law of the slow step is consistent with the experimentally determined rate law. So again, you're only going to use that equilibrium business when the reactant, or the reaction before the slow step was an equilibrium reaction, and if that's an intermediate that was produced in the equilibrium reaction. So follow?
Do we actually have to write all that out? Or can we just, like, when we explain, do we...
I should see something about the fact that that was produced in equilibrium. You don't have to write it all out. You should acknowledge that that was changed to that because it was an equilibrium. Maybe just say, because equilibrium, and then go on. That's fine. Okay. Ellen, did you have a question too? You raised your hand.
Yeah, I was wondering if it had to be an equilibrium equation.
It has to be, yes. In order to be able to use this thing right here, this K. Yep. Okay, so we're moving along. Now, again, I'm going to mechanism 2. This is not valid because your slow step just has an F2 term in it, and the slow step needs both of these terms in it to be valid. And this was not produced by an equilibrium, so I can't go above it and find anything else. You see what I'm saying? So this is not a good one. Let's try another example, can we? Anybody have any other questions about this?
How does the equilibrium constant work again? How did you know to do it? Is it just reactions?
Yeah, it's products over reactions. Yep, yep. And that ratio is a constant as long as the temperature stays the same. Yep. And this number is a constant as long as the temperature stays the same too. So a constant times a constant, as long as we're not changing the temperature, they're still equal to a constant. I call it K prime. The next one, I believe, is number 6 that we're going to do. I'll tell you which one it is. No, I'm sorry, number 4. If you'll jump back to number 4 with me. Now, this is another one that was taken from an old AP exam. It's got the same font as all the AP exams have.
The font is not.
It's the College Board. What do you expect?
Yeah, it's.
Nasty fonts
Yeah, it's like too small.
for nasty people. All right, so let's take a look at number 4. Is number 4 a nasty one?
No, not really.
Ah, yeah, it is.
Yeah.
Why is it nasty?
Because it doesn't keep it the same.
One of the reactants is never held constant. Why do they do that? If you're going to run multiple trials, how about keeping the reactance constant, at least in 2 trials.
Because they're the college board.
Okay, which one is easier to find the order of?
BR2.
The BR2 is, because the NO is held constant at least in 2 of the trials. So use trials 1 and 2, find the order of BR2. Is it easy? What's the order of BR2? First order, yes. Because in trials 1 and 2, the concentration of BR2 is doubling, and the rate doubles. So that means the BR2 is first order. Are you with me?
Oh, no, just.
Close enough?
It's like 0.1 off.
All right, so take your calculator and divide. The trial 2 rate divided by the trial 1 rate, what do you get? Okay, yep, it should be. So 0.000638 divided by 0.000324. 1.97. Not good enough for you?
No.
0.97.
Okay, then you're on your own. Yeah, it's good enough for me. And, you know, if you want my help, then it should be good enough for you too. All right, anyway. So yeah, it's close. BR2 is first order. So now I want to take you over back to this. If we know that BR2 is first order, I'll put it first right there. That means that, let's see, which 2 trials do you want to use to try to find this one's order?
1 and 3.
1 and 3 maybe? Okay, fine. So when the BR2 gets cut in half, what do you expect to happen to the rate? It's going to get cut in half. What's half of 3.24? 1.62. Everybody okay with that? So the influence of the BR2 being first order would cause that rate to go to that. Now you want to do this. As the NO doubles, what's happening to the rate? It's going up by 4. That's right. Close enough to quadruples?
No.
Close enough.
I think so. Would we agree that this is second order then? Because doubling the concentration causes the rate to quadruple. So the rate law is, let's see, the rate law consistent with the data is way down here. Rate equals K times NO to the second power times BR2 to the first. Yeah? That's what we do with those. All right, now what are they asking here for in A and B? Calculate the initial rate of disappearance of BR2 in experiment 1. Well, how are they defining the rate? They're defining the rate based on the appearance of the product. So for part A, what is the rate of disappearance of BR2? Do you see how it's a 1 to 2 ratio? So if this is going up at a rate of 3.24 times 10 to the negative 4th, how fast is that going down? Half that fast. Yeah. For every one of these used up, 2 of those are made. So if that's going up by a certain rate, that's going down by half that rate. It's a 1 to 2 ratio. Okay? When you're looking at the relative rates, when you're comparing the rates of one thing in the reaction to another, you've got to use the coefficient ratios. But when you want the rate law, you're using the data. Yes?
So it's just a coincidence that the coefficients are the same as order.
That's a coincidence, yes. Vincent, that's only a coincidence.
Yes.
Okay, all right. Good call on that. Yes. All right, number. I love it when people say that. Number B. Determine the order of the reaction with respect to each. Oh, I guess we already did that. In each case, explain your reasoning. Now, if this is the actual AP exam, can you do that? Can you explain your
Do we
reasoning?
have to explain it in like words, or can we just write the equation, or like just show them that?
Either way, I think it's fine.
Could we just draw an arrow up to that thing?
No, because there's an answer document. They're not checking this.
Okay.
You're going to have to do it on a blank sheet of paper with lines.
Yeah.
And you're going to, yeah. You'll have to say that, experiment or trials 1 and 2, the NO is held constant, that doubled, causing that to double. That was first order. You have to write that out or show that mathematically somehow in a timely fashion. For this one, you'd have to say, oh, I used trials 1 and 3, while this one cut in half, we corrected the rate to that number, and then that quadrupled as that got doubled. So yeah, you'd have to explain that somehow.
All right.
So this one's going to take you a couple minutes to work through. All right, now, part D. The following mechanism was proposed for this reaction. Is this mechanism consistent with the given experimental observation? The first thing you want to check for is, do you add these steps together to get the overall equation? Let's see if that's true. Just canceling out that intermediate, you're going to have Br2 plus 2 of those yields 2 of those. I think that part's consistent. And is the slow step rate law consistent with the experimental rate law?
No. Because there's no 2
Is
I
the
know.
slow step here rate law consistent with the experimentally determined rate law for the overall reaction?
No.
No! Because the slow step must have 1 Br2 and 2 NOs in it. The slow step must. Remember, the rate is all determined by the slow step. It's the molecularity of the slow step. The molecularity of the slow step in this proposal has 1 Br2 and 1 NO. That's not consistent with this. It's got to have 2 NOs in it.
Wait,
Yeah, the coefficients didn't matter.
For the steps in the rate law, they do. For the overall, they don't. When you're analyzing a mechanism and you have steps in the reaction goes through that step and then it goes through that step. You look only at the slow step and what we call the molecularity, which is the colliding molecules and the reactant molecules in the slow step. They must reflect the overall rate law for the reaction. This step is not the same thing as the overall reaction. The overall is all these steps added together. And those coefficients don't allow us to know that.
So if those 2, I know of the top, then.
Yes, if that had a 2 in it, then it would be a valid mechanism. Nathan, not catching that?
No, I didn't.
Okay. Andrew?
So is this the same thing time from the reading, please?
Yeah.
Okay.
Yeah. So if this were the mechanism, you'd say that the rate law is k times that to the first times that to the first. But that doesn't agree with experiment.
You just said it didn't matter.
The overall coefficients don't matter.
Yeah.
I'm saying that these coefficients up here for the overall reaction don't matter. When you're looking at a mechanism, the coefficients in the slow step do matter.
So
This
the-
is called the rate determining step, and it's the rate law of that slow step, which
So-
is, go ahead, I'm sorry.
When you're finding the rate of like that one step, you just do like BR and then just raise the coefficient.
Yes.
Okay.
Yep. That's right. Okay, well, I'm glad we did that one. Okay, I don't know if you gathered this much out of the reading. This is essential, you have to know it. The rate law of the slow elementary step. So the slow elementary step rate law is just based on the molecularity of what's colliding. It's just the coefficients on the reacting things in the slow step that determines the rate law. So these two things have to be true for a mechanism to be a valid proposed mechanism. They have to add up to the overall reaction, and the rate law must agree with what you found in the experiment.